Hello everyone, we are Group 6 and today we will explore the volume of sphere. Our presentations have 4 parts. First, background informations. Second, method analysis. Third, curriculum design. And last, conclusion. For the volume of sphere explorations, a problem that fascinated mathematicians for centuries, we will look at its history and method by Liu Hui, Zhu Gen, Archimedes, and Cavalieri. By the end, you will see how ancient math shapes modern math. The volume of a sphere was studied in ancient Greece, China, and India. It was a challenging problem due to the complexity of 3D geometry. This work reflects advancements in mathematics, astronomy, and engineering. Different civilizations solved the sphere volume in unique ways. Archimedes in Greece used exhaustions. In China, Liu Hui approximated pi, and Zhu Gen created a volume principle. In India, mathematicians gave practical approximations. This idea shaped modern geometry. Eastern and Western math solved the sphere volume differently. In China, Liu Hui and Zhu Gen focused on practical methods. In Greece, Archimedes used logic and geometry. Both approaches make big contributions, show math is universal. For the education value, studying ancient methods like Archimedes' work on a sphere teaches critical thinking. He compared a sphere to cylinder to solve complex problems. This helps students think creatively, break down challenges, and see math as living, developing subject. Practical applications. The sphere volume formula, V equals to 4 over 3 pi r cubed, is used everywhere. In physics, it calculates mass and density of planets and nanoparticles. Engineers use it for water tank and sport equipment. Architects design domes and curved structure with it. Ancient math still solve modern problems. Ancient math, like Archimedes' work, inspire modern research. Their idea in geometry and calculus help fields like computer graphics, where 3D shapes are key. Studying their work honors their contributions and shows that learning connects us across time. The sphere volume bridges educations, innovations, and cultural heritage, providing its timeless relevance. Now, let's explore a method of these mathematicians. First, Liu Hui's circle cutting method for approximating pi. Next, Zhu Gen's principle for calculating the sphere volume. Finally, we will compare Zhu Gen's and Cavalieri principle, showing Eastern and Western approaches. The timeline shows their contributions. Liu Hui and Zhu Gen worked in ancient China. Archimedes was in Greece, and Cavalieri in Italy. Despite different times and places, they all advanced our understanding of the sphere's volume. For the inspiring quotes, Liu Hui said, "The finer the divisions, the smaller the error." Archimedes says, "Give me a place to stand, and I will move the earth." Zhu Gen said, "If cross-sections are equal, volumes cannot differ." This quote shows the timeless power of math.
There are 3 parts of method analysis. First, exploration in ancient China. Second is different paths of Eastern and Western mathematics. Third is bridging ancient wisdom and modern mathematics. First, the basic principle of Liu Hui's circle cutting technique. Liu Hui thought of increasing the number of sides of circle connected to the square polygon. He has applied the ideas of limits to calculation approximations. Second, Liu Hui's exploration and Zhu Gen's principle. Liu Hui also found that the ratio of the area of the sphere to that of its tangent circle is 4 to pi. It is deduced that the ratio of the volume of the sphere cone to that of its tangent circular cone is also 4 to pi. Liu Hui pointed out that the determination of the volume of the special curved body formed by the intersection tangent cylinders in a cube is also the key to finding the curved bodies. Liu Hui's observation was inherited and finally in the 5th century was satisfactorily solved by Zu Geng, who had obtained a principle, 密室即同则计不容易. And next is Zu Geng's limit breaking and proof. Consider when is stem as solid and place it inside a square with side length equal to the radius r of the sphere. Because of the volume ratio, we finally get the volume of the sphere is 4/3 pi times r cubed.
The Italian mathematician Cavario introduced Cavario's principle in his work Geometry of Indivisible Quantities. Influenced by Cavario, Cavario focused on the geometry study of motion and change. His idea directly inspired the development of calculus by Newton and Leibniz. Cavario's principle stimulates the concept of indivisible volumes, providing an unfilled framework for calculating volumes. The core idea of Cavario's principle is that if two solids lie between the two parallel planes and have equal cross-sectional area at every height, their volumes are equal. This principle simplifies complex volume calculation by comparing cross-sectional area, laying the groundwork for integral calculus. Notably, Cavario's principle shares a striking similarity with Zu Geng's principle from ancient China, as both rely on the equality of cross-sections to deduce equal volumes. Cavario applied his principle to derive the formula for the volumes of sphere by studying the cross-section of the hemisphere and cylinder with the cone removed. He observed that at any given height, the cross-sectional area of hemisphere equals to a cross-sectional area of the cylinder minus the cone. According to Cavario's principle, since the cross-sectional are equal, their volumes must also be equal. Despite being developed thousands of years apart, Zu Geng's principle and Cavario's principle both rely on the geometry intuition that equal cross-sections imply equal volumes, laying the foundation for integral calculus. This reflects the University of Mathematics choice across civilization. Ancient Chinese mathematics, which is deep understanding of infinite divisions, provide important insight for future generations, even though it did not develop a symbolic theory. The core idea of the ancient mathematics, such as the accumulation cross-sections to find volume, are highly compatible with the modern integration technique like the slicing method, demonstrate the foresight of ancient wisdom. Ancient mathematicians solve complex problems through the three-step process of division, recognition, limits, which continues to inspire modern mathematical innovation. Although ancient mathematics did not develop an abstract symbolic system, its intuitive geometry solution remain valuable example for the study of the history of modern mathematics.
Next, the links between ancient thought and modern mathematics, the principle of complementarity and the idea of integral division, the cross-sectional area proportionality method, and Cavalier's principle. Last is the ancient limit to the calculation of approximations. Bridging ancient wisdom and modern mathematics. First is math innovation and thinking outside the box. Second, cracking the complex problems through the three steps of fractal reorganization and limit. Third, combining the geometric intuition and algebraic calculations.
Then I will introduce the curriculum design. The volume of sphere is the content of the second compulsory mathematical course in senior high school, and the teaching object is grade 2 students. The topic not only provides as a continuation and intention of knowledge related to cylinders and cones, but also lays the foundation for solving practical problems related to spheres in the future. Before learning this content, students should be familiar with the volume formula of cylinders and cones. Understand this shape how they build a foundation for compare with spherical volumes. The fundamental of mathematical modeling. This skill is important as it enables students to translate real-world problems into mathematical terms. And about the teaching difficulties, one of the major difficulties is understand formula derivation, particularly when using Zugen's principle. Many students struggle to master the concept of equal volumes. Another challenge is spatial imagination ability. This limitation hinders their understanding of geometry principles and make learning more abstract. By the end of this lesson, students will be able to understand and master the concept and apply it to the real-world problems. Second, using Zugen's principle to derive the volume formula of a sphere. Last, let students know the significant status of Zugen's principle in Chinese mathematical history.
So our teaching design is associated with the 5E model of instruction. The 5E model of instruction includes 5 phases: engagement, exploration, explanation, elaboration, and evaluation. And this class we decided to take 40 minutes to teach students. In the first phase, teacher can let students to review the surface area and volume formulas for cylinders, primes, and pyramids that they have learned before, according some worksheet before the class. Then introduce the new content to be learned through some story about stemite solid and Zugen principle, 密室既通则机不容易, like the content mentioned in part 2. In the exploration stage, teachers can ask students to find the volume of the stemite solid based on the Zugen principle, and give some hints to help students learn, such as telling them to divide the stemite solid into 8 parts and do the calculation in one of them. Students can also have group discussion. After discussion, teacher explains through algebra animation to help students deepen their understanding. Therefore, in classroom exercise, teachers can ask students to prove the formula again based on their understanding of the previous content to deepen their understanding, and give them a related exercise to strengthen their memory of the sphere volume formula. In the evaluation stage, teachers can assign relevant exercise as homework, like these 2 exercises. During the process, we can use algebra to illustrate that why the volume of sphere is smaller than the volume of the stemite solid, and the arrow in 9th chapter of arithmetic. And during the explanation phase, they found that the volume of 1/8 of the stemite solid is equal to the volume of a cube with the same side length, as the radius of its inscribed circle subtract the volume of the pyramid with the same side length. That is, the volume of the stemite solid is equal to 3/16 r to the power 3, and because we know that the ratio of the volume of the sphere to the volume of the stemite solid is 4:pi, we can get that the volume of the sphere is 3/4pi r to the power 3.
The last part is conclusion. In the first 3 parts, we have introduced the background information, which taught us the history and significance of sphere volume calculation. Then, method analysis compared East and West thinking about how to calculate the volume of sphere. And finally, we try to integrate it into the curricular design. The study of sphere volume has evolved significantly over time. Ancient Eastern mathematicians like Zugen focused on practical methods, while Western thinkers like Archimedes emphasized logical proof. In modern times, calculus and computer simulations have further refined and expanded these calculations, bridging the gap between historical intuition and contemporary mathematical rigor. Ultimately, mathematics is a universal language, and the exploration of sphere volume exemplifies how different cultures have contributed to our understanding of geometry and beyond.
We would like to discuss why integrating history of math in such a topic. Incorporating math history enriches education through 6 core strengths. First, conceptual depth. Tracing ideas like Jugen's value calculations clarifies modern principles. Second, engagement. Humanizing math via stories of Archimedes or Liu Hui sparks curiosity. Third, critical thinking. Analyzing historical problem-solving fosters innovation. Fourth, cultural insight. Celebrating global contributions from Greek geometry to Chinese algebra. Broaden perspective. Fifth, role models. Perseverance of past scholars inspire education. Sixth, interdisciplinary links. Integrating math history connects mathematics with subjects like history and philosophy, encouraging interdisciplinary thinking. However, challenges exist. Time constraints impact curricula, insufficient teacher training, and varied student interest can hinder effective integration. Traditional assessments also struggle to measure historical understanding. To address this, educators must enhance professional development through workshops and resources. Strategically design curricula to balance history and core content. Utilize multimedia and storytelling to engage diverse learners. Adopt innovative assessments like projects or reflective essays to evaluate holistic understanding. In conclusion, integrating math history, rich past and present, transforming learning into a dynamic, interdisciplinary journey.
Then we would like to ask, how can future classrooms integrate math education with math history? Firstly, we need to improve teaching methods for more interactive learning, such as inquiry-based learning, storytelling methods, and so on. Secondly, utilize modern technology for an enhanced learning experience, like geometry softwares, 3D modeling, AR and VR for immersive learning, etc. And thirdly, setting up diversified assessment strategies is quite necessary. Our last reflection is about what mathematical thinking and skills can we develop from studying math history. The answer is diverse and meaningful. For example, we can develop logical reasoning for strengthening the ability to prove and derive mathematical concepts, or build up mathematical modeling by practicing turning real-world problems into mathematical ones. Other skills such as abstract thinking, problem-solving thinking, creative thinking, interdisciplinary thinking skills can also be well trained. This is the end of our presentation, and thank you for your patient listening.